So what is thermal spray? It's a generic name that covers a whole gamut of processes, much like arc welding covers quite a few processes with arc welding. But the main thing is it uses a source of energy to produce heat and kinetic energy to melt the coating material and propel it as substrate, producing a coating. Here in this little diagram, you see it's got the heat source here. You're injecting your powder or your wire. It's heating it and propelling it at the substrate. It tends to be a series of little small splats. In most cases, you're not completely melting the material. You're just heating it to a plastic state and propelling it at the substrate. Each one of those little splats, when it hits the substrate, it goes splat, and then all the other ones come in behind it. So the more kinetic energy you have, the tighter those stick together, the denser the coating, the less the porosity, which a lot of the coatings are used for sealed surfaces and corrosion resistance. So having a good tight bond between all of them with no porosity cuts down on issues with leak paths and corrosion. I guess whatever corrosive material, you don't want it to get to the substrate. If it finds a leak path through porosity, you'll start getting rust under your coating. It'll disbond and everything goes bad. Before I leave this picture, probably the most important thing along that is the dwell time that the material is in the flame. If you don't give it enough time, you don't get that plastic state, and most of the material will hit the substrate, and since it's not plastic, it's going to bounce. And a little bit later, I'll show you a picture of the guy actually spraying by hand, and he's wearing a hood, and it's because it's annoying when you're spraying this if all that bounce is coming back and it just pecks at your forehead, and it drives me crazy. The other end of that spectrum, if it's in the flame too long, you overheat and you oxidize and you ruin the properties of the material that you're putting down. So the actual spray distance is very critical, and that's one of the reasons it's good to automate. Like I say, there's a whole gamut of processes. I'm just going to cover three of the more common ones. That's actually the ones I'm the most familiar with. The first one being HVOF. It's a high velocity oxygen fuel process. You can use liquid fuels or gas type fuels. And basically what it is a small rocket engine. You're injecting your fuel and your oxygen into a combustion can. You got a small continuous combustion, usually around 120 psi. And then converging diverging nozzle, which basically takes all that pressure, sends it down, and right as it's expanding, it creates a low pressure area where you can inject your powder. That's super critical. As that nozzle wears out, you start getting your pressure at your point of powder injection gets a little high, and then you start messing up the rest of the process. So the diverging nozzle, that's one of the more important things with that particular deal. HVOF, it tends to have low heat, and that's a relative term because it's still hot, but it's much less than like plasma. Where that's good is applying like stainless steels and Inconels, your corrosion-resistant alloys. You're not over-oxidizing. Same with your carbides. You're not oxidizing the actual material. On the other end, it does have high kinetic energy, so your splats are held together tighter. They're less porosity, higher hardness. Flame velocities, they've clocked them up to 7,200 feet per second. And while I didn't put up there, most of your materials like carbides, they travel about 33 to 3,400 feet per second. And just to put that in relative terms, a bullet coming out of just a standard deer rifle is somewhere around 3,000, maybe 3,100 feet per second. So it's going pretty good. The process, it's usually used for just basic metals and carbides. Like I said, less than 1% porosity, high hardness. With the carbides, it's not uncommon to see 1,200 DPH, 300 gram load hardness, so it's pretty dense. Next process, plasma. High heat. Again, it's relative. It's compared to the other, it's much higher. It's you can get temperatures up to 50,000 degrees Fahrenheit. Why is that important? Ceramics. They use them for dielectric properties, seal surfaces. We actually used them in food processing. We'd spray a ceramic and then apply a Teflon over it, so you got, like we called it, a wear release coating. But I guess going back to the plasma process, the big difference in it and the others is we're not burning a material, we're using an electric arc. And I guess the big difference in this and what most people, when you think of plasma, you think of plasma cutting or plasma welding. In those processes, you're actually transferring the arc to your substrate. In this one, where the arc is actually staying with the torch, not transferring to the part, we're just creating an arc using ionizing gases to push that arc out of the torch a little bit to where we can inject our powder and heat it and propel it at the substrate. And it's it can do the it can apply metals, different metals, stainlesses, Inconels, cobalt materials, carbides, and ceramics. It does all of them well, but its real strength is in handling the ceramics. You won't get the same hardness and the same porosity that you would with the HVOF. HVOF beats it on porosity. And the other one I'll talk about is twin wire arc. This one, we'll say it's a high heat. It's nowhere near what plasma is, but here, instead of just heating the coating material to a plastic state, here we're actually forming arc. We're actually melting it. With most welding, you have a ground clamp on your work, and you have, in your electrodes, you've got the other, and you're passing through. Here, we're actually putting positive voltage on one wire, negative on the other, bringing them together, creating an arc, and then sending compressed air through the center to atomize that and spray, propel it at the surface. So it's really good. It's really easy to set up. It does really good. We're spraying different alloys, for corrosion and dimensional restoration. But again, it doesn't have the kinetic energy that you get from the HVOF process. So it tends to be used on more like bond coats or corrosion resistant coatings. I'm sure everybody's heard of aluminizing. That's what it is. You got two aluminum wires come together and you're spraying it on there. It's really good for, they'll use it a lot in the field to protect bridges and different structures and so forth. More I can really say about that other than the equipment tends to be, as far as setting up a process, this is one of the more economical ones to set up. You basically have a power supply, a pair of wire feeders, and compressed air, and you're good to go. So you can take it in the field and do it. So now get to why we're here. Why automate all this? The biggest reason would be operator safety. All these things I'm talking about, either having flammable gases or electric arcs. 80 volts, 500 amps, not something you want to hold in your hand all day. So put it on a robot and take care of all that. The next thing would be the coating quality and efficiency. Talked about how the spray distance is so critical and the angle at which you spray. And then the last would be the ease of processing your parts. I put the first HVOF gun on the robot for the company I used to work for back in '93, but I programmed it the hard way. I programmed it point by point, so it would take me 2 or 3 hours to set up for one job, and we'd spray it in 2 hours. So it was kind of, unless you were doing a repeat, it didn't really make sense, but I'll show you an easier way to do it later in all this. All right, so earlier I mentioned the picture of the operator wearing a hood. You see, you can't see, he's got earplugs in his ears. He's wearing a P100 respirator, safety glasses on. He's got a glove, but to protect his hand. But in that hand, he's got oxygen, propylene, nitrogen, all flowing through his hand, coming out the end of that torch. On that particular system, the flame velocity is a little less, probably in the 6,000 feet per second range, but still, it's a little rocket motor, and he's holding it in his hand. So, you know, when you're running it by hand, you're exposed to loud noise, extreme temperatures, flammable gases, the fumes, and the particulate. The particulate's really bad because all the metals that you're applying, they're all not stuff you want to breathe. A few of the guys that were in the thermal spray industry, back when I first got in, we've had a couple of them that have succumbed to pancreatic cancer, and I kind of feel it's probably from exposure to some of this stuff. The last thing down there was the rotating part. I forgot to mention that. He's spraying a chrome carbide on a fuel nozzle of a cow cap. It's for a power generation turbine. But that part, it looks like you'd think it's all secure, but it's actually just sitting on that chuck. The part is too thin. You can't really grab it, so it's just sitting there. But it's spinning about 200, 250 RPM. So it's a little unnerving to stand there by it. All right. I kind of got ahead of myself a little bit earlier, but with the, when you automate, put this on a robot, then you have really good, precise control of your motion control. You can maintain your torch angle, your spray distance, and your travel speed. With most of your thermal spray processes, your deposit efficiency is typically 50, maybe 60%. Some of them up in the 70s. But if you put that in perspective, if you're spraying a carbide powder that's roughly about $75 a pound, HVOF you're spraying somewhere in the 10, maybe 12 pound per hour range, and only half of it is sticking to the part. It's a problem. So you do it by hand, and where you can't really control all these things really tight, that drops even lower. So it's really important to control your torch angle, 9 degrees. You get off that much, then it changes everything. Your DE drops, your porosity goes up, your hardness goes down, all the bad things. And then the other one, the process control. Your spray parameters. We were looking at plasma a while ago. I've kind of briefed over it real quick, but you've got voltage, you've got amperage, you've got a primary gas, a secondary gas, the pressure coming in, your material feed rate, how many pounds per hour you're spraying, as well as your carrier gas pressure and your carrier gas flow. I forget how many different parameters are with plasma, but you change one of them and it gets a little bad. You change 2 or 3 of them and it goes to pieces on you, and trying to figure out which ones just went out. Different combinations make it really hard to maintain a good coating process. So by automating, you control motion control, and you control the process control. Keeps everything a little tighter, makes it run more efficient. I mentioned the way I programmed the first gate valves, point to point, and everybody would go home and I'd stay there, program the robot so they could run the next day. Well, there's a much easier way of doing it. Instead of programming a couple 100 points, program 1 point, because your fixture's in the same place every time. Your part's going to be in the same place. And you just, you program that 1 point, and the rest of your points are just offsets. It's just simple math. And robots are good at math. Let it do the math. After this evening, after all this is over, I'll be doing a demo over here of spraying a ball valve. And these variables here are all that I have to tell it when I change size of the ball valve. I just have to tell it the diameter of the ball valve, the centerline distance of the ball valve from the chuck, how many degrees of spray do I want to carry around the part, and the minimum speed. I'm not as worried about the maximum speed because you really can't go too fast, but you can go too slow. most of the coatings like to maintain your hardness and not build up too much stress within the coating. You want to keep your you don't want to pick up more than about 1,000 per pass, and most times you'll see it where it's really a half to maybe 3/4 of 1,000. But put it on in multiple thin layers, and it adds up to a good coating. So just changing those 4 things, and I can go from ball valve to ball valve to ball valve. So it's a 5-minute setup as opposed to a couple of hours. Yeah, and in case you're not able to come over there after the event, I'll show a video of it. Johnny, you told me if I pushed the button, it would do it. I did. I pushed the button. That's when it flipped. Okay. Here you see the robot come on, and we're traversing across that part. Looks real simple, and it relatively is. But what you've got to be concerned with is the difference in surface area. On the 2 ends of the robot, close to the flow bore, you've got a smaller diameter. And in the middle, you've got a larger one. So to put that coating on evenly, you're around the outside, you need to travel fast and then slow down and then come up fast again and come off the part without staying anywhere too long and building up heating everything. Oh, okay. I was gonna say it wasn't supposed to loop. I guess the thing to with ball valves is, being a sphere and it's you're putting the coating on to create a seal surface. It's usually direct lapped after you apply this coating. So you want to put it on as even as possible. You need to keep your thickness tolerance within about 1,000th of an inch. You get over that much more as you're lapping it, trying to get the high spot down. You're going to grind through on the other, and then you've got to start over. The next one, these are just simulated gate valves. This is like what I was programming back in '93. And here, you'll notice I've got one point right here, and the rest of it is all offsets from that point. Oh. So there's that point. Now it's just doing offsets. And what it's doing is going across, it's coming up and stepping in, basically just traversing across the part. After they're coated, gate valves are typically run across a surface grinder with a diamond wheel, and then they're lapped. So the coating thickness isn't as critical as a ball valve, but for every 1,000th of coating you put on there, that's another 1,000th that you've got to take off with a diamond grinder. So it's expensive putting on, it's expensive taking it off. So you try to keep it down to a minimum. Most of the gate valves, they typically apply the coating, looking for a finish thickness at 7 to 10 thousandths thick of the carbide after grind and lap. So to do that, to get 10 thousandths, I've got to spray, I got to put 12 to 13 on it. Now with the robot, I can hold that flatness across that part within 1,000th and a half. But with the coating, the first couple of thousandths is kind of what we refer to as just kind of fuzz. It's not, doesn't have all the other splats coming down on it to make it dense and then increase the hardness. So first couple of thousandths are kind of fluff. You got to take that off and then get down to the good. So, and I think that should be, that should be it.